In the prior session, we had an overview of target trial emulation. Here, you will find yourself more comfortable because here I will discuss specific topics, specific problems that we found with COVID-19 vaccines studies. And then after this, Susanna and Ellie will do the real thing and present applications. So this talk will be 35-40 minutes, and we'll have 4 parts. First, I will try to discuss the differences between sequential emulation and just using a time-varying exposure for your study. Then we'll have a few slides to discuss how to differentiate between safety and effectiveness of our vaccines when some of the effect might be mediated by prevention COVID-19 disease. Then the third part will be about how to handle follow-up when all the controls get vaccinated. And then the fourth one will be about challenges that we're facing and how we are addressing those. So sequential emulation versus time-varying exposure. I added this slide because I just had a conversation right now about causal inference, prediction, description. Target trial emulation is a causal inference exercise. And it's important to differentiate causal inference from other tasks that we do with data science. When we have data, we can do 3 things. We can just describe our data. For example, what's the percentage of pregnant women who received a vaccine in 2021? That's a descriptive exercise. You just summarize your data, easy peasy. Then you have predictive questions, where you just have to map some features of the world to other features of the world. This is what Netflix does with you when they recommend your next movie, or Amazon, or I don't know, Google with advertising. They just analyze you and use that information to predict what you need in your next purchase or movie. That's not causal inference. But then we have causal inference questions, which is, what is the effect of doing this? What if we do this or that? So the difference with these 3 tasks is that the type of data and the type of methods that we use are different. Description, you just describe. For prediction, you just map some information to other information. You don't care about confounding. You don't need to adjust for anything. You just have to be good at predicting something. But in causal inference, as we saw with the causal diagrams, we need to be careful with confounding. We need to be careful with selection bias, etc. So that's what makes causal inference different. So many of the projects in Back4You started with primary vaccination, right? And the first step was getting the causal question right. So we had to evaluate whether vaccination was safe, but compared to what? Compared to other vaccines, compared to no vaccination. Then what is COVID vaccination? Is just receiving 1 dose? Is it receiving 2 doses? Is receiving 1 or 2 doses? So you have to be very specific on your question to map the analytical steps and the design steps that we will come later. So for the exercise that we're going to do now, we're going to address this question, which I think is a common question in some of our projects. What is the causal effect of receiving at least 1 dose of a COVID vaccine compared with no vaccination on the risk of ISIS, right? Calendar time, as you know, is very important because during our study periods, calendar time was associated with the probability of getting COVID because there were waves. This is a representation of the waves in Spain from January 2021 to January 2022, 1 year. Different outcomes, deaths, ICU admissions, cases. There are waves. So depending on your calendar time, you have different probability of having the outcome. And calendar time is also associated with the probability of getting the vaccine because vaccines were deployed, and then more and more people got the vaccine. So the probability of getting the vaccine also changes with time because there were policy changes about who to vaccine. So that's the definition of a confounder. And we can draw a causal lag because we already explained what is this. A is vaccination, Y is our adverse event, L is calendar time. So if we know this confounder exists, we have to adjust for that. And in a DAG, I think I didn't say this, when you condition on something, you put a square on it. And that represents that you block this backdoor path. So this is the causal structure of baseline confounding due to calendar time. And you adjust for that somehow. How did most of the studies adjust for calendar time? By individual matching. All the studies that I presented before, published in New England, in Nature, Lancet, they adjusted for calendar time for this baseline confounding by matching. So whenever there was a vaccinee, at that very same calendar time, they picked up unvaccinated people. That's matching on calendar time. So this is the table, a generic table of the target trial emulation that we would design if we want to estimate the effect of receiving at least one vaccination or no vaccination, right? Those would be our vaccination strategies. The eligibility criteria would be people with an indication for primary vaccination. Our target trial would randomize people to these strategies. The outcomes are the adverse event of interest, whatever it is. The per protocol effect can be the effect under full adherence to the vaccination strategy. So if you are in the no vaccination strategy, you are not supposed to get a vaccine during the follow-up. Okay, so how can we do that? Well, we can just match on calendar time, which is something that we do in many of the Back4EU protocols, something that they did in all those academic exercises that I showed you, published in the New England, Lancet, Nature, etc., which was just matching on calendar time. When you do that, you are comparing vaccinated this sounds obvious, but you will see the difference now. Vaccinated individuals with unvaccinated individuals, right? You're matching on calendar time, which is a confounder, but by matching you're adjusting for that, you are safe. The problem here is that if you emulate a single trial by choosing only 1 times 0 in your whole study period, you might not have a lot of information here because you're taking only people vaccinated here. So, okay, you can do that, and you have to come up with a way to choose your control. The exposed individual is the vaccinated guy, and you have to pick a control for that. There are 4 options here. You can just choose everyone who was not vaccinated that day. Why not? There will be confounding by other variables, but you can measure those variables and use your preferred statistical approach to adjust for that. You can use inverse probability weighting, standardization, whatever. The problem here is that this can result in a large database, and you can end up with computational problems because of the size of the database. And one way to dimensionalize your database is choosing only one control. Instead of choosing everyone who wasn't vaccinated that day, you just choose one. Who should I choose? Okay, you can just choose one at random, and your database will be smaller. Still, you need to adjust for baseline differences. You can use the same approach as before, whatever you want. A third option is to inform somehow who you're gonna choose by trying to choose someone who is very similar to the vaccinee based on the propensity score. The propensity score is the probability of being vaccinated or not vaccinated, conditional on all the baseline variables, all the confounders. You can use that to pick a very similar control to your vaccinee person. The problem here is that to estimate the propensity score, you have to run a model in the whole country, in all the unvaccinees. So whenever you pick a vaccinated person, you have to run a propensity score model on everyone who was not vaccinated that day.
On every day.
We have not there yet. Don't go so fast. We're here. We are not doing sequential emulation yet. We're just doing one.
On time zero. So you are doing that on time zero.
Yes, on time zero here on all these guys. Then I'll talk about sequential emulation. Well, we do this many times. I'll get there. Okay, so you can do a propensity score, but you have to do that model on everyone who was not vaccinated that day. And that can also be burdensome. And a fourth option is what was done in those manuscripts that I show and what is being done in many projects, where you matched based on a number of variables. So you identify individuals based on the value of a number of variables that you think are confounders, but you don't use any model. This is still a computationally challenging procedure because you have to identify everyone, measure all the variables, and then do a matching. But it's easier than running a model on everyone. Okay, that was about who to choose. Now, if I do this only once, by choosing a single calendar time, this is not very efficient because I'm discarding everything that happened here and everything that happened here. So to use all the information in the whole study period, I can emulate a sequence of trials. So I can do this every week or every day of my study period, right? And this is what we do, what was done in those studies and what we do in many of our protocols. We just emulate in a sequence of trial where each day eligible patients who have not been vaccinated, in theory, in the target trial, are randomized into getting the vaccine or remain unvaccinated. And a new trial, a new target trial, starts every day of my study period, and that day is the time zero for the new emulated trial. And this is how it works. We emulate a number of trials, starting from time zero until defining time zero at the beginning of my study period, and then the last trial has the time zero at the end of my study period. The causal structure of my target trials here is the same. I will have baseline confounding at each time zero. So each baseline I have to measure the eligibility criteria and I have to measure the characteristics of the patients and do something to adjust for that. Because I'm using individuals more than once, I have to take that into account when I estimate the variance. Okay, now, some people might think, I'm not familiar with sequential emulation of trials. I'm more familiar with just treating vaccination as a time-varying exposure. And you can find this method in many pharmacoepi studies where there is only one time zero. You assess eligibility only once here, and then people can be unvaccinated for a period of time and then turn into vaccinated for another period of time, right? So vaccinator is coded as a time-varying exposure that goes from 0 to 1 at some point, right? Then you use one model, one outcome model, a Cox or a Poisson model, where you throw in that time-varying exposure, and that model gives you a hazard ratio, which is a time average hazard ratio of being ever vaccinated versus never vaccinated, right? This could be an approximation to a per protocol hazard ratio that we would obtain with the sequential approach. which target trial are we emulating here? The target trial here would be, I'm recruiting everyone here, and I'm randomizing the time to start the drug. So this start of the drug happens at random in my target trial. This approach is used because the data management is simpler. You just have a set of eligible people. You don't have a sequence of eligible individuals. So data are easier to handle, but there is a problem. So the causal structure of the sequential emulation was very simple. Yes, baseline exposure, baseline confounding, the outcome. I only need to worry about baseline confounding. Now, here, my model contains baseline exposure and post-baseline exposure, right? And I will have baseline confounding, and I will have variables that are also confounders of subsequent exposure, and that can be affected by prior exposure. So, okay, now you know DAX, so you can solve this. Do I have confounding here? Do I have common causes of the exposure and the outcome? This can be a common cause of A0 and Y. That's confounding, right? Okay, I can condition on this. I can put this in my model. I will be adjusting for this, and I'm conditioning on this, and I'm blocking this backdoor path. Good. Let's move to T1. Do we have confounding here? L1 is a common cause of A1 and of Y. So that's confounding. So let's adjust for this. I add L1 to my model as a time varying covariate, and I am adjusting for this. So I'm blocking this backdoor path, right? What's the problem here? Anybody sees the problem?
Because my causal question is from A0 to Y, right? That's the causal question. The association between A0.
No, A0 and A1. You're getting a hazard ratio for the whole thing. Both exposures are in your...
The association between A0 and Y.
That's one thing. But...
Are you using people or person time?
Periods. We are comparing periods, person time. We are comparing person time.
So one person is contributing from A0
And then changes to... And A0 can be, the value of A0 for an individual can be 0 unvaccinated, 1 vaccinated. The value of A1 for that same individual can be 0 or 1 unvaccinated or vaccinated. The problem is L1 here, because L1 is a collider. Because it receives arrows from A0 and from U, and a measure confounder of this confounder and Y. When you condition on a collider, you introduce bias. In the DAG introduction that we said before, we said we can have common causes, you need to adjust for common causes, or you can have common effects. When you have common effects, you get into trouble when you condition on common effects. If you are entering L1 in your model to adjust for it because it's a confounder of A1, you are opening this path because it's a collider of A0 and U, and you are introducing an association that shouldn't be there by doing that. Is there an alternative? Yes. To deal with that, you can use G methods. You can use time varying adjustment. You can use inverse probability weighting. Inverse probability weighting works by creating weights that change over time and are a function of prior confounders. And when you use those weights to weight your population, you create a pseudo-population where exposure at every time is independent from prior confounders. So you get rid of this arrow and of this arrow. By getting rid of this arrow, this is not a confounder anymore. And this is not a confounder anymore. So my point is that Data management is easier when you treat your exposure as a time-varying exposure because you don't have to create a sequence of trials, but your causal structure is different, and you need to know that, and you need to use appropriate methods to deal with that.
Sorry. L1 could be, for example, mild or non-severe COVID infection when we are studying hospital severe infection.
No, AR is the exposure.
But the
L1. L1 can be
severe infection.
L can any yes.
Severe infection when you are looking for severe infection.
Can be any variable that you think can affect your probabilities of getting a vaccine and your probabilities of having an outcome. Good. This is why I just explained. Your causal structure is different, so you need to use more complex methods. I'm all in to use complex methods. That's fun, but just know that can be complicated. Another problem is that you will only get a hazard ratio. You will not get curves, Kaplan-Meier curves. You won't have absolute risk or absolute differences on the risk. And this is a summary of we just said. You have two options. You can emulate a sequence of trial, and at every time-varying factors are extracted at each time zero, so they turn into time-fixed confounders at the beginning of each trial, as opposed to this scenario where time-varying factors are time-varying confounders, and you need to use more complex methods. So, let me ask you a question. Imagine you have four studies, and investigators in each study used a different design, and you get these results. Study 1, the hazard ratio for the AESI is 1.00. Study 2, they give you a risk difference at time t, which is an excess of 4 cases per 100,000 individuals. Study 3 gives you a hazard ratio of 1, and study 4 gives you a risk difference at time t of 0 cases per 100,000 individuals. So which one doesn't look very safe? Study 2, right? Well, these are real results from our own studies. And study 1 and study 2 are the same study, and study 3 and study 4 are the same study. Why is that? Because a hazard ratio is an weighted average of the ratio of the hazards during the whole follow-up. So you can have a curve like this one, which is a real result, where for a period of time, the risk of having the AESI in the vaccinated is lower, but then it increases. So at the end of the follow-up, there is an excess risk. But the average hazard ratio is 1. So if you are using a method that doesn't let you draw your cumulative incidence curve, you're losing a lot of information. And that is an example where both the hazard ratio and the risk difference at the end is a null effect. These are real results. In our day-to-day practice, in our projects, we use the graphs a lot. We look at them all the time to see whether they make sense or not. Sometimes we see weird shapes that it's clear something's going on, and we use that to ask the DAPs, what do you think of this? Do you think there can be something or not? And we have used this to identify problems with the code or with the data extraction, and we have fixed those. So Kaplan-Meier curves are a very, very useful diagnostic tool. You cannot get this with the time-varying exposure. You get this with the sequential emulation. Okay. Second part, safety and effectiveness. When we estimate the effect of a vaccine on adverse events, some of the effect of the vaccine might be mediated by the preventive effect on the infection by the virus. For example, if respiratory failure is one of our ISEs, the vaccine might protect against that because it protects against the infection, which in turn causes respiratory failure. If the vaccine actually has an adverse event, which is respiratory failure, this can be masked by the protective effect of the vaccine against the infection. So there are different approaches in the different studies that have been published, but everything boils down to differentiating the total effect versus the direct effect. I'm not advocating for any of them. I just want to explain that those two effects exist, and you can use different methods to estimate each of them. Just explain what you are doing. The total effect is the effect of the vaccine on the adverse event through all causal pathways, both a direct effect and both the effect that is mediated by the prevention or the effect on the virus. The problems with the total effect is that if COVID-19 is really a mediator, the effect will depend on the circulation of the virus. If there is no circulation of the virus, the effect will be different than if there is a high circulation of the virus. The direct effect is this arrow. So before, the total effect is the effect from A to Y, both through D and directly to Y. The direct effect is only from A to Y. So it would be a trial where we vaccinate people and we lock them in a room and they have no contact with the real world, so they cannot get infected, right? How do we emulate that in an observational setting? By censoring them if they get the infection. And you will see that in some of the papers out there. That's why they censor when they have a COVID infection. You have to do additional assumptions to justify that there is no bias, because what did we say about colliders before? D is a collider, we're conditioning a collider. So you can introduce selection bias, or you have to make additional assumptions to justify that you are identifying the direct effect. Okay, handling of follow-up. I know this was a headache for many of us in many of our protocols, because over time, over our study periods, the proportion of vaccinated increased a lot. Like, this was a situation that pharmacoepidemiologists had not seen before ever. Never in the history of healthcare intervention something was deployed at such a massive scale as COVID vaccines. So the problem was that you had a vaccinated group, which were vaccinated, good. You cannot get unvaccinated after you are vaccinated. But then in your unvaccinated group, it gets contaminated with vaccinated people over time. So you want to estimate the effect of vaccination versus no vaccination under full adherence. You have to do something. And you have two options. You have the option of just censoring them when they get a vaccine. And you have the option of, if you have used matching, removing both the vaccinee in the control group and the corresponding vaccinee in the exposed group. So what are the advantages and disadvantages of each approach? When you keep all vaccinated, you have more data. You have more precision. But you need an additional analytical step, because that censoring can be informative, right? So you need to use, for example, time-varying inverse probability of censoring weighting to deal with that. And you have to make some assumptions that conditional on the match variables and on the time-varying covariables, the weighted population of uncensored individuals, in other words, those who remain on your database and not being analyzed. You are assuming their risks are similar to that of the censored individuals had they not been censored. That's one approach. The other approach is censoring the pair. By censoring the pair, it's analytically easier. You don't need to use time-varying weights, which can be a burden, computationally speaking. You will have fewer data, less precision, and the type of assumptions you have to make are stronger, because before you assume that based on two sets of variables, baseline and time varying, they were similar. Now your assumption is stronger. You assume that conditional only on the matched variables, they are similar. I was never sure which was the best approach, and I'm not sure yet. And this year in ISPE, this work was presented. This had to be taken with a grain of salt because it was an oral presentation, it's an abstract, it's not a full paper yet, and the simulation they use is relatively simple. But what they did was using simulated data to compare these approaches. So they simulated data in a relatively simple simulation, 100,000 individuals. The hazard of events changed over time, and 80% of the unexposed group gets vaccinated over time. And they simulated this under a null effect. So the intervention has no effect. And they compare the different approaches. This is the base case where they show there's no effect. This is what they simulate. This is the approach where they just censor the unvaccinated if they get a vaccine and they don't do anything else. And it's clear that they are getting a bias estimate. The second scenario is censoring the unvaccinated plus inverse probability of censoring weighting, time varying weights. So here they get something that is closer to the true. So it looks like this approach works. Approach 4 is censoring the pair, which is something that is in some of our protocols. This also works. And the fifth scenario is both censoring the pair plus inverse probability weighting, and that also works. So it looks like single censoring doesn't really work. You need to do something else, either censoring the pair or use weights to adjust for that. But as I said, this is an abstract in ISPE. I'm looking forward for the full paper. Okay, let's finish with one of the challenges that we are facing and that Oisin already mentioned yesterday, and that we're working with him and Zeynep and people at RTI, which is estimation of the variance. The second part of my talk was about sequential emulation versus time-varying exposure. I think sequential emulation is the way to go because that gives you cumulative incidence curves, which are a must, I think. But that induces autocorrelation because individuals can contribute more than once to your analysis. So the standard estimators of the variance don't work because there is repeated individuals. You need to use an approach that takes into account autocorrelation. One alternative is the robust variance estimator. This is conservative. Go ahead.
Can I ask a question? Because if you would censor if they change treatment, also you have one involved people maybe multiple times, but you only have that period of time once. So you don't double count days, correct? So if they would go from an unvaccinated to a vaccinated, but there can be multiple candidates.
Somebody can have more than one time zero. And somebody can be in the comparator group today and in the exposed group tomorrow.
Yes, but that's what we like in classical epi would call density sampling also. Your time count is not your person ID.
No.
Then you stay in the analysis. And there are days that are counted twice.
Yeah, so now you...
And this is especially true for those persons who have a specifically rare combination of covariates among the unvaccinated. So those that are typically persons that would be expected to be vaccinated, then they are sampled as control 10 times.
Yeah. Plus, please.
Sorry, but if we are discussing, I think we are people online.
So maybe we can discuss at the end and we put around the microphone. Okay. Okay, so one approach to a correct estimation of the variance is using the robust variance estimator, which is conservative, usually wider than it should be, but it covers the true effect more than 95% of the time. But this is not available for risk differences or risk ratios estimated via a Kaplan-Meier estimator. So I think we should use curves, cumulative incidence curves, but the robust estimate of the variance doesn't give us the variance for the risk difference of the risk ratio using curves. Alternative 2 is bootstrapping, which is our nightmare, because bootstrapping means doing your study a few hundred times, literally. You have to do the whole thing, applying the eligibility criteria, the matching, propensity score, or whatever, everything 500 times. So if our databases are large and our commitment with regulators are tight, we have a problem. So here is where we are. So what we are doing is I'm calling ourselves, Oisin, Zeynep, and RTI guys, a task force. We are trying to come up with a creative approach of how to do efficiently all the repetition of this study a few hundred times, trying to create steps where we store all the information needed and then drag from there the information we need for each of the runs, etc. And this is work in progress. And the second approach, which is something that is embedded in the ROC20 and that we are doing with Svetlana, who's there, which consists on identifying the most expensive step of the study, which we think is matching, and substituting it with an approach that is less computationally expensive. In our case, we are changing matching on calendar time with a random sampling of time zero and just putting that into the adjustment model. This is something we're working on. This is something that won't impact immediately other projects, but will inform future design and future analysis, and I think it will be a great piece of publication. And this is all I had. Now we can discuss while you scan the QR code for the course in Barcelona in March. Okay. Questions? Oisin.
It's working. Switch it. Another one. Put it on with it.
Yeah, okay, great. So I understood like the Kaplan-Meier curves, you said you were adjusting for calendar time in this analysis. So calendar time was your confounder, L.
Mm-hmm.
So what's the interpretation of these Kaplan-Meier curves? Is this like the survival curves marginalized over calendar time? Is it assuming that the difference in survival is the same for all calendar time? So how would you deal with something like effect modification, where really the effect of vaccination on the outcome is different over calendar time?
Yeah, these Kaplan-Meier curves are built by pulling together all the sequential trials. End of the story. So it assumes there is no effect modification by calendar time on the adverse event, which I think it's a safe assumption.
All right, thanks.
Thank you very much. Although all what you have tried to do is you've done your best looking at all the options and you tried. The problem with the COVID comparative cohort, there was so many things that happened to it that one could stand by and say, should we compare it all? Initially, only the above 80s, the vulnerable people, you're talking about January, February 21 were vaccinated, and then the others started to vaccinate very quickly. Then countries stopped vaccinating all those below the age of 60, all those below the age of 40 because of thrombosis and so on. And then what the messages passes about the vaccines and so on. The comparative cohort became so complex that if you do propensity score, you're left with a very small proportion of the total cohort to deal with. Does it represent the real world? So, it was so problematic that all the strategies which you applied really couldn't cope with the changes in the comparative cohort.
I think that's a great point, and that's a problem of positivity, right? That you need to have a representation of your exposure in all the levels of the potential confounders. That is something that you have to live with, and there will be situations where there won't be a solution, there won't be a fair comparison, and I take your point, 100% sure. Svetlana.
In Target trials, matching is always done on the start of exposure. But why is it better than matching on event date? So as a nested case control study.
Okay. No, that's a great question. The application that I showed about statins in the prior talk was a target trial emulation, a cohort study. We match at baseline, or we identify people at baseline, we follow them, etc. There is a follow-up publication that uses the same statin example to do a target trial emulation using a case control design. What we do, our point of view there is that case control is a way of sampling from an underlying cohort. So the underlying cohort must exist. And then you sample from there. You sample the cases and you density sample the unexposed individuals. And that will give you an odds ratio that corresponds to the causal hazard ratio. But you need the underlying cohort. So all the trouble that we went through to create a sequential emulation of trials, expose and expose, is there when we do a case control study. But then we case control sample from that underlying cohort. So my answer to your question is that case control is a way of sampling from an underlying cohort, and the problems that you have in that cohort study are also present in your case control study. So when we did that target trial emulation using a case control design, we also used time varying weights to estimate the per protocol effect, etc. I don't know if I answered your question. I hope I did. Rosa, because she has the mic.
And because it's me.
Okay.
What about self-control designs?
I don't know how to emulate a self-control design with target trial emulation. And for the rest of the audience, this is like the 10th time that Rosa asked me this question. And I always answer the same. When I figure it out, I will let you know. I'm not saying it's impossible. I'm saying I don't know how to do it.
There is work to do there.
Yes. Romin?
Me and Rosa, so psychically aligned.
Okay. Good.
Hi, thank you. Is it on? Yeah, thank you so much for the presentation. Because in the sequential trial design, you already mentioned that it's kind of unprecedented that there's so many people quickly got vaccinated, so we are running out of the control quickly. And then at some point, if you continue the sequential trial longer, you will end up with a certain group of people who will never get vaccinated no matter what, and they might get higher chance constantly being included as a control. And I wonder if that's a problem or not, and if it's so, like, what should we do?
Yeah, I think that can be related to the prior question where you end up having very weird population with a set of characteristics so unique that they won't be represented in both groups. One of the assumptions that you do in every observational study, not in target trial emulation, in every observational study is positivity, which is that the exposure needs to be represented in everyone in both groups. In this specific case, we can run into that problem, that people are so different that there is no way to adjust for that. And that's a problem. You have to be aware of that and stop the study or restrict your study to a different study period, take measures. Yeah.
Yes, Xabi. So just to elaborate a bit more on what Sad was asking, like now that we know, for example, that there were risk minimization activities, no? So for the AZ vaccine and later on, would you then, if you would do a comparative between two active, so not between vaccinated, non-vaccinated, but for example, between Pfizer and AZ, would you then say, this is going to be an effect modifier, I start all my, like this is that a different, how would you treat it? Like, would you create like a split in calendar time to before and after and do that comparison again? Or would you define different no, it's not a treatment strategy.
So I know it's not polite to answer a question with another question, but what is your target trial? Who would you be randomizing? And if we can write down a target trial, that's our comparison.
But the comparison would stay the same. So the comparison would be those that get a Pfizer vaccine versus those that get an AstraZeneca vaccine. So that question doesn't change. It's just that over calendar time, those that get AZ and Pfizer may change. So they are different over time. Yes. So we need, and this is what I say here, that that time-varying risk factors, which is what you are saying, become time-fixed confounders in the sequential emulation. So at the beginning of each trial, we extract the baseline variables. So the trial that we emulate here, the population that we include here might be very different from those that are included in a trial emulated later in the study period. But at the time zero of this study period, I'm extracting also all the baseline variables, and I'm assuming I'm able to use those baseline variables to adjust for the difference, to adjust away any confounding effect. So you would adjust for confounders, but you cannot take away effect modification that may exist. So would you recommend that?
Well, you can, when you estimate your outcome model, if you think there is effect modification, there are ways to deal with that. You can add interactions and estimate your effect in these specific populations if you think the effect is very different. If there is a strong effect modification, there is no point in estimating an average effect. Imagine the effect is very different in men and women, then we need to estimate the effect in men and in women. Vera?
Thank you. I'm just wondering also on a practical note, in that left figure, you have time 0, 1 and time 0j, and if that period of time is short, can you just get away with measuring baseline covariates at time 0, 1 and assume that maybe they don't change, especially in our real world data? Or is it also a matter of population changing over time?
That's a question that I cannot answer. That's a question that somebody expert on the data should answer, whether that makes sense or not. That's making an extra assumption, yeah. Estelle.
Can you go back to the Kaplan-Meier curve? Okay. In this Kaplan-Meier, basically, you cannot calculate the HR because the assumptions of proportionality doesn't hold. But in these studies where everybody got censored pretty soon, the idea was to calculate the estimates at the end, like at 1 year. But for most of the studies, there will be no one that it takes 1 year, like you censored them before. Does it make sense to have different time points where you estimate and report the estimates?
Well, the curve gives you all the time points. The curve gives
That's what I mean. If it makes sense to look at the data to decide on the time points where you want to report the results.
Provided it's not the client.
As long as it's not, as long as it is not an interested picking of the...
Because usually we say it at day 365, and we have nobody and we have no precision. So a posteriori to say, okay, instead of at the end or the last patient alive, we will do at...
I don't see a problem. As long as you give the curve, you're being transparent. You say, this is the point estimate. Then you're giving the difference here, there, and there with the confidence interval, because you feel those are good representations of the effect on your data. I think that's fair.
Just a quick comment on the confidence interval. As you were saying earlier, they may be conservative if we use robust variance, so that's a problem of course, type 2 error. So I think that also really looking at the curves and maybe some diagnostic of the a long time, some diagnostic of the cohort, right? So that at some point, in some day, I mean, there is a drop in the control or whatever. That's also maybe useful somehow and interpret this graphical.
Yeah, and thank you, because there is something I didn't put here for confidentiality, but below the curve we always have the people at risk, and that is also a very useful diagnostic because it lets you see whether there is a drop here and there and is it expected or not. I didn't put it here.
Because statistical significance is
exactly.
up to some point.
Hi, a slightly different question. I'm just so curious. So when you conduct this study and draw the Kaplan-Meier curve, so for example, like when people die and then death prevents people from experiencing any ASI, I'm just curious what you do with people like that, and how did you incorporate it in your target trial or in your estimate?
Thank you. That's a competing event question. That is not related to target trial emulation, but it's a problem of data analysis, not only observational data analysis. You have that in clinical trials, you have also in observational data. You have, the approach is similar to the approach I saw for effectiveness and safety. You have to be explicit about whether you are estimating the total effect, the effect of your vaccine on whatever outcome that can be mediated to the effect on death, or the direct effect, which would be the effect had nobody died. This estimate is a little weird because you're giving a number in a world where nobody dies, but in this world people die. So you have to take that with a grain of salt and explain your assumptions, etc. That's a competing event problem. Yeah.
I have a question from Angela Lupatelli, who's joined online, about pooling of estimates in a sequential trial. Can you please explain which method is used for pooling?
So when we have done sequential trial emulation, what has been done is just putting, and this is related to Oisin's question before, just analyzing all the database together. You assume that the sequential emulation, the effect is the same across all the emulations, and then you analyze all the data together. It's not that we estimate one effect for each trial and then we meta-analyze them. It's that you put them in the same database, assume the effect is the same, and get an estimate.
So thank you for this fascinating presentation. I have one question and one comment about this slide. The question is not about this slide. The question was about the question, how would you represent the self-controlled case series? And I was thinking about this, the best thing I could think of is an open label study, which is, of course, a long way from the randomized control trial. But then I was thinking open label, one aspect of the randomized clinical trial, the so-called gold standard that you have not been talking about, is the blind, actually. And here we're actually in an open label. People who are vaccinated, they know that they are vaccinated. So since you have been thinking a lot about what you can gain by thinking about an observational study in terms of randomized clinical trial, is this blind or double blind that we do not have in observational studies? Can we do something about this, or would that lead to some methodology? Or I have no idea, actually, but since you seem to have a lot of ideas, maybe you have.
No, there is nothing you can do about blinding. So when you emulate a target trial, that target trial is a pragmatic trial, a trial where there is no blinding. The patient knows what he or she is receiving, and the follow-up, etc., is according to standard practice.
Thank you. And then the comment about this one, your question, I know the question is to go through the Kaplan-Meier, but I would never accept a question like that. I would not discuss what is safer, because then you want to think about in terms of benefit risk, but also you don't present any of confidence interval. And for example, 4 cases per 100,000, you may well have a very large confidence interval, which would be compatible with the odds ratio or the hazard ratio. And then when I want to see whether a study is giving concern or not, I would actually look at the upper limit of the confidence interval. But that's a general comment.
That's a good point. And next time I present this, I will delete the confidence interval and I will say it's 3 million individuals. So it's a thought experiment. It's just to highlight the value of a curve. Thank you.
Thank you.